In general relativity, gravitational effects arise due to space-time curvature or space-time geometry. So one of the first things we need to do is to learn to describe geometry in mathematical terms. So let's start with the most simple situations and describe the geometry of various two-dimensional spaces, 2D spaces. So for example, we have the Euclidean plane. So that's just the geometry of a sheet of paper. Another example is the sphere. Now when I refer to the sphere, I'm referring to the two-dimensional surface. So we're ignoring the interior. It's just the surface of the sphere. Another example that we'll talk about is a horse's saddle. So a horse's saddle looks something like this. Okay, let me make a few comments about these examples. The first comment is that these are two-dimensional spaces, whereas our space-time is four-dimensional. So these are 2D, not 4D, as our space-time is. Second comment is that notice these are really spaces and not space-times. And we'll see later on the distinction between a space and a space-time. And the third comment is that notice in each of these examples, the spaces have been depicted as surfaces. In other words, they're two-dimensional subspaces of a higher dimensional, three-dimensional space, which actually we assume in these pictures is Euclidean. So these are surfaces or subspaces embedded in a higher dimensional space, which is implicitly 3D Euclidean space. So this is different from space-time. Space-time is four-dimensional, and as far as we know, it is not embedded in any higher dimensional space or space-time. Now let's take a closer look at the Euclidean plane. How do we describe the geometry of the Euclidean plane? Well, the geometry satisfies Euclid's axioms. So, for example, parallel lines never meet, and the sum of the interior angles of a triangle equal 180 degrees. I like to imagine ants walking along the surface. So here's one ant starting out in this direction, and another ant starts out in this direction, parallel to one another. Now, if these ants just walk straight ahead on the Euclidean plane, their paths will never cross. Well, we have another ant who walks straight ahead, turns through some angle, walks straight ahead, and then closes his path as a triangle. That ant can measure the angles of the triangle, and they'll add up to 180 degrees. Okay, so those are some of the unique characteristics of the geometry of the Euclidean plane. Now let's consider the sphere. Our ants can do the same experiment. Here's our two ants, and they start out moving parallel to one another, but eventually those parallel lines cross. In fact, the way I've drawn it here, they meet at the North Pole. We have another ant who traces out a triangle, so the ant walks straight ahead, then turns, walks straight ahead, makes one last turn, and closes the triangle. If the ant measures these angles, they add up to something other than 180 degrees. So you can see that the geometry of the sphere is distinctly different from the geometry of the Euclidean plane. Now, let me make a few comments. First of all, this notion of the ants walking straight ahead, either on the plane or on the sphere, this is well defined. So the ants simply put one foot straight in front of the other and keep their eyes straight ahead and simply walk. And this notion of walking straight ahead, it's referred to often as walking in a straight line, even if the geometry is curved. We refer to that as walking in a straight line. And we'll make this mathematically precise later on. And the second comment I want to make is that notice the ants are probing, in these cases, what we refer to as the intrinsic geometry. Intrinsic. The intrinsic geometry is distinct from what we refer to as the extrinsic geometry, which refers to the way that the surface is embedded in the higher dimensional, three-dimensional Euclidean space. So let me give you an example. We can take our piece of paper, which we know has a Euclidean geometry, and we can bend it so that it has a little hill. And now we can put our ants on this piece of paper that's bent like this, and we can have them do the same experiment. The two ants start walking parallel to one another. They'll walk up and down over the hill, and these parallel lines will never meet. Okay, we have another ant who traces out triangle, which now looks a little bit distorted because it's on this bent piece of paper, but the sum of those angles still add up to 180 degrees. And this is clear. After all, I could have drawn the red paths and the red triangle on the piece of paper when it was flat and then bent it to make the hill. So the difference between this piece of paper and this piece of paper is not a difference in the intrinsic geometry, it's a difference in the extrinsic geometry. So the way we quantify that is we look at the normals, the unit normal vectors, and we can see that here on the bent piece of paper, these normal vectors are not parallel, whereas the normal vectors on the piece of paper, when it's laying flat, they're parallel. So this is a distinction between what we call the extrinsic geometry. So between these two pictures, the difference is extrinsic, the way that these two-dimensional spaces are embedded in the higher dimensional, three-dimensional space. But the intrinsic geometry is the same in each case. Now, in the case of space-time, as far as we know, space-time is not embedded in any higher dimensional space or space-time. So when we talk about the geometry of space-time, we're referring to the intrinsic geometry. geometry of space-time is intrinsic geometry. So how do we define mathematically the intrinsic geometry of a space or space-time? Well, the geometry is defined by what's called the line element. Okay, and the line element gives the distance between neighboring points. And for this purpose, we need to introduce a set of coordinates into the space. And we can use any coordinates we like. The geometry is independent of what coordinates we choose. So we need to choose coordinates to express the line element. But the geometry is independent of the coordinates that we choose. So, for example, let's start with the most simple possible case, the case of the flat Euclidean plane. Let's introduce Cartesian coordinates. Okay, x, y. So here's some generic point. X comma y. Here's a neighboring point. X plus dx, y plus dy. Okay, and the distance between these 2 points let's call that ds. So this is the distance between neighboring points. And we know how to write down the distance between that. It's just given by the Pythagorean theorem. It's the square root of dx squared plus dy squared. All right, this is usually written as, by squaring both sides, as ds squared equals dx squared plus dy squared. So this is the line element for the Euclidean plane, two-dimensional Euclidean plane in Cartesian coordinates. Now this line element encodes the internal geometry of the space. So from this expression we could derive Euclid's axioms that parallel lines never meet, the sum of the angles of a triangle equals 180 degrees, and so forth. Now, we chose to write down this line element, we chose Cartesian coordinates, but we could have just as well chosen some other set of coordinates. For example, what if we decided to use polar coordinates? R and theta. Okay, so polar coordinates are related to the Cartesian coordinates by x equals r cosine theta, y equals r sine theta. And if we write out the line element in polar coordinates, we find ds squared is dr squared plus r squared d theta squared. So this is the line element for the Euclidean plane in polar coordinates. So this describes the same geometry as this line element. The only difference is the difference in coordinates. Now there are a couple of different ways that we can derive this line element for flat space Euclidean plane and polar coordinates. One is to just simply draw a picture of polar coordinates. So there's the radial lines. These are the r equal constant curves. And let's call this point, this point has coordinates r comma theta. And here's a nearby point with coordinates r plus dr and theta plus d theta. Then the distance between those 2 points, which again we call ds, we can find that distance again using the Pythagorean theorem. So it's the square root of the sum of the squares of these two legs of this triangle. So this distance right here is dr, that's dr squared, and this distance is r d theta. So if we square that, that's r squared d theta squared. Okay, so now square both sides and you have this as the line element in polar coordinates. Another way that we can derive this result for the line element in polar coordinates is by starting with the line element in Euclidean coordinates and using these relations. Okay, so from x equal r cosine theta, we can compute dx so dx is dr cosine theta plus, or rather minus, r sine theta d theta. And from y equals r sine theta, we have dy equals dr sine theta plus r cosine theta d theta. And now we write the line element Cartesian coordinates and just substitute these expressions for dx and dy. So this is dr cosine theta minus r sine theta d theta quantity squared plus dr sine theta plus r cosine theta d theta quantity squared. So now we multiply these out. We have first dr squared cosine squared theta, and squaring this we have r squared sine squared theta d theta squared, and then there's a cross term minus 2 dr cosine theta r sine theta d theta. From here we have dr squared sine squared theta plus r squared cosine squared theta d theta squared, and then the cross term is 2 dr sine theta r cosine theta d theta. So you'll notice these cross terms cancel. These terms that multiply dr squared, we have a cosine squared plus sine squared, which is 1. And here we also have sine squared plus cosine squared, which is 1, and we're left with r squared d theta squared. So this is the result for the line element in polar coordinates, derived by using the coordinate transformation on the line element in Cartesian coordinates. So the line element is always expressed in terms of some coordinate system, but that coordinate system is up to us to choose, and we can choose it any way we like. It doesn't affect the geometry that the line element describes. So just to emphasize this point, let's write down the geometry or the line element for the Euclidean plane using some strange coordinates. Let's define coordinates alpha and beta by the following coordinate transformation. Let x equal alpha plus beta and y equals, I don't know, beta divided by alpha. Okay, what does the line element look like for the two-dimensional Euclidean plane using alpha and beta as coordinates? Well, we can work it out just like we worked out the line element in polar coordinates. Dx is d alpha plus d beta. Dy is 1 over alpha d beta minus beta over alpha squared d alpha. And now we can plug that into the line element in terms of Cartesian coordinates, and we have d alpha plus d beta quantity squared plus 1 over alpha d beta minus beta over alpha squared d alpha quantity squared. And we can multiply that out. Let me go ahead and do that. This is d alpha squared plus 2 d alpha d beta plus d beta squared. And from the second term we have 1 over alpha squared d beta squared minus 2 beta over alpha cubed d alpha d beta, that's the cross term, plus beta squared over alpha to the fourth d alpha squared. And we can collect these terms together. The d alpha squared terms look like 1 plus beta squared over alpha to the fourth d alpha squared. There are d beta terms, d beta squared terms. That's 1 plus 1 over alpha squared d beta squared. And now there are cross terms that are proportional to d alpha times d beta. We have 2 times 1 minus beta over alpha cubed d alpha d beta. So this is the line element for the flat Euclidean plane in alpha beta coordinates. And if we wanted to work hard enough, we could prove Euclid's axioms using this line element. Parallel lines never cross. The sum of the angles of a triangle add up to 180 degrees. So what does the line element for a sphere look like? We can derive this without too much difficulty using spherical coordinates. So spherical coordinates theta and phi. So here are curves of constant phi and curves of constant theta. All right, let's look at two nearby points. Say this point and this point. So this is the point theta comma phi. This is the point theta plus d theta comma phi plus d phi. If we do that, this distance right here is, let's say the sphere has radius a. Then this distance is a times sine theta d phi, and this distance is a d theta. Okay, and then using the Pythagorean theorem, because these two segments are at right angles, this distance ds is square root of a d theta squared plus a sine theta d phi squared. Okay, so squaring both sides, we have the line element a squared d theta squared plus a squared sine squared theta d phi squared. So this is the line element for the two-dimensional sphere in spherical coordinates. And we could, of course, pick another set of coordinates if we like and express the line element in those coordinates. It would still describe the same two-dimensional geometry. As a final example, let's look at the line element for the horse's saddle. All right, well, and here's the horse's saddle once again. We can define the horse's saddle. Well, let's use the fact that we're depicting this as a two-dimensional surface embedded in Euclidean three-dimensional space. And let's define the horse's saddle to be the following surface. Let's just say it's the surface, and here's my z, x and y coordinates in the three-dimensional embedding space. And let's define the horse's saddle to be the surface z equals y squared minus x squared. Okay, so as if x is 0, as y increases, z forms a parabola. The z increases to form a parabola. That's this curve. And for y equals 0, this curve here is a parabola pointing downward. Okay, so we'll just use this to define the horse's saddle. All right, well, if we want to know now the line element for this horse's saddle, what we can do is we can use the fact that we define this as a surface embedded in three-dimensional Euclidean space, and in three-dimensional Euclidean space with Cartesian coordinates x, y, z, the line element is dx squared plus dy squared plus dz squared. This is the line element for the 3D embedding space. And now we can use this relationship to find dz in terms of dy and dx. All right, so dz is 2y dy minus 2x dx. And now plugging that into the line element for the embedding space, we have dx squared plus dy squared plus the quantity 2y dy minus 2x dx quantity squared. Simplifying that, we'll have a 4x squared dx squared term, so combined with that, we have 1 plus 4x squared times dx squared. Similarly, the dy squared terms, we have a 1 from here and a 4y squared from here. And then we also have the cross terms from squaring this. That would be 2 times this term, so that would be minus 8 times x, y, dx, dy. So this is the line element for a horse's saddle defined by this relation in terms of the embedding space coordinates. And what this is telling us is the geometry of this horse's saddle in terms of coordinates x and y that can be thought of as the projections of the xy coordinates from the plane up to the surface. Of course, we could use different set of coordinates to describe the geometry of the horse's saddle. The line element would look different, but it would still describe the same geometry. One thing we can do with the line element is to compute the length of curves. So let me give you a very simple example. Let's go back to the Euclidean plane with our Cartesian coordinates. So we know the line element looks like ds squared equals dx squared plus dy squared. And let's consider the half circle. So we'll take a half circle of radius, say 3. So circle begins here at x equals minus 3 and ends at x equal plus 3. All right, first of all, how do we describe this curve, this half circle? Well, one way is to parameterize it. Let's introduce a parameter lambda, and then we can write this curve as x as a function of lambda is equal to minus 3 times cosine of lambda, and y as a function of lambda is 3 times sine of lambda. And in this parameterization, lambda ranges from 0 up to pi. Okay, so as lambda ranges from 0 to pi, we sweep out this curve. Okay, now to compute the length of the curve, we just need to use the line element to find the distance between some point on the curve, let's call this the point lambda, and a nearby point lambda plus d lambda. Okay, once we know that distance, then we just sum up all those distances. In other words, we integrate. Okay, so the calculation is simply use these expressions to compute dx and dy. So from here, we have dx is equal to 3 sine lambda d lambda, and dy is 3 cosine lambda d lambda. This gives us the change in x and y as we move from this point to this point. All right, so ds squared. Well, first let's write ds. Okay, ds is square root of dx squared plus dy squared. And using our expressions for dx and dy, this is 3 sine squared lambda, 3 times sine lambda quantity squared d lambda squared. That's the dx squared, plus 3 cosine lambda quantity squared d lambda squared. Okay, so simplifying, this is just square root of 9 d lambda squared, or in other words 3 d lambda. So this distance right here is 3 times d lambda. And now to get the total distance through the half circle, we just integrate. So the total distance s is the integral of ds. That's the integral of 3 d lambda, and the range is lambda equals 0 to pi. So that's just equal to 3 pi, which is of course the correct result. One thing that's important to recognize is that there's nothing really special about this choice of parameter lambda that I used to parameterize the curve. We could choose another parameter. For example, let's replace lambda with, I don't know, say lambda squared. So we'll parameterize the curve in this way. X is minus 3 times cosine of lambda squared. Y is 3 times sine of lambda squared. And we'll let this new parameter lambda range from 0 to square root of pi. Okay, so it's this parameter, this new lambda, ranges from 0 to square root of pi. These parametric equations for x and y sweep out this half circle. All right, and we can now compute the length of this curve in terms of this new parameter, and we should get the same result because it doesn't matter how we parameterize the curve. The length of the curve is a property of the geometry, and it's independent of that choice of parameter. So let's go ahead and do that calculation quickly. We just need to compute dx and dy from these expressions just like we did here. Okay, so let's, if we can remember, x is minus 3 cosine lambda squared, then dx is 3 times sine lambda squared times the derivative of lambda squared, which is 2 lambda d lambda. So simplifying that, we have 6 lambda times sine of lambda squared d lambda. And dy is 3 cosine lambda squared times 2 lambda d lambda. That simplifies to 6 lambda cosine of lambda squared d lambda. And now we compute the distance s, which is the integral of ds. All right, so that's ds is just the square root of dx squared plus dy squared. So dx squared is 36 lambda squared times sine squared of lambda squared times d lambda squared. And dy squared is 36 lambda squared times cosine squared of lambda squared times d lambda squared. Okay, and now you see we have a common factor of 36 lambda squared times d lambda squared in both of these terms. We have sine squared of something plus cosine squared of something is equal to 1. So this is the integral of square root of 36 lambda squared d lambda squared. And by the way, the range, remember, is from 0 to square root of pi. So simplifying, square root of 36 is 6, square root of lambda squared is lambda times d lambda. And now it's a simple integral. This is 6. The integral of lambda is lambda squared over 2. And we're integrating this from 0 to square root of pi. So this is 3 times the square root of pi squared minus 3 times 0 squared, which is 3 times pi. Of course, the correct answer. So we've now computed the length of the half circle and shown it to be 3 pi using two different parameterizations of that curve. And of course, we could also use different coordinates. Both of those calculations used x and y, the Cartesian coordinates in the Euclidean plane. But we could use, for example, our crazy alpha beta coordinates. X was equal to alpha plus beta, and y is equal to beta divided by alpha. So what we could do is we could write the curve as alpha as some function of some parameter, beta a function of some parameter, then use that with the line element in terms of alpha beta coordinates to compute ds and then integrate. And of course we should find the same answer, 3 pi, because the answer doesn't care what coordinates we use, just as it doesn't care what parameterization we use. Let me sketch out a little bit of how this calculation would go. We could use the parameterization that we already had. Let's use the cosine lambda as opposed to cosine lambda squared. Y was 3 sine lambda. And now we can find these expressions for the curve for alpha and beta as functions of this parameter lambda by just inverting these relations. So how would we do that? Well, let's see, this expression tells us that beta is equal to alpha y. So if we insert that into the first expression, we have x is equal to alpha plus alpha y. So that's 1 plus y times alpha. So then alpha itself is written in terms of x and y as x divided by 1 plus y. And now that we know what alpha is, we can find beta from this expression. Beta would be x times y over 1 plus y. So the curve, in terms of this parameter lambda, would be minus 3 cosine lambda over 1 plus 3 sine lambda, that's alpha, and beta of lambda is minus 3 times 3, that would be 9 times cosine lambda times sine lambda over 1 plus sine lambda. Okay, and from here we can compute d alpha. That would give us some expression times d lambda, and also d beta. That would just be the derivative of this with respect to lambda times d lambda. Now insert these results into the line element. If I remember correctly, the line element in terms of alpha beta coordinates was something like 1 plus beta squared over alpha to the 4th d alpha squared, and so forth. Okay, we can insert these expressions for alpha, beta, d alpha, and d beta into the line element. Of course, take the square root of both sides and then integrate. I'll leave it to you to fill in all the details, but the answer you should get, of course, is 3 pi. How do we define a straight line in a curved geometry? So this would be the path that an ant takes if the ant just puts one foot in front of the other and just walks straight ahead without turning to the left or the right. Okay, this is referred to, a straight line is referred to as a geodesic. And it's defined as a path or curve that minimizes or maximizes the distance between 2 points. All right, so let's look at our most simple example, 2D Euclidean space with Cartesian coordinates, x and y. Okay, a generic path or curve is defined by giving x and y as functions of some parameter lambda. And we know how to compute the distance along the curve. We need to compute dx and dy in terms of d lambda. And let's, since these are generic paths, this is, well, just dx d lambda, dy d lambda, d lambda. Let's denote dx d lambda by x dot. So the dot refers to differentiation with respect to lambda. And then dy is just lambda dot d lambda. Sorry, dy is y dot d lambda. Okay, now we insert this into our expression for the distance along the curve. ds is square root of dx squared plus dy squared. dx squared is x dot squared d lambda squared. So this is square root of x dot squared plus y dot squared d lambda. And the integration goes from the starting point, let's just call it say it has a parameter value lambda 1, and the final point, let's give it a parameter value lambda 2. So this is the general expression for the distance along a curve between lambda 1 and lambda 2. Now, in order to minimize or maximize this expression, this is just like the process of finding Lagrange's equations from the action principle. We just vary the action, or vary the distance in this case, with respect to x of lambda and y of lambda. Okay, so this is integral from lambda 1 to lambda 2. Varying this expression, we have 1/2 1 over the square root of x dot squared plus y dot squared times 2x dot delta x dot plus 2y dot delta y dot, and all of that is times d lambda. Okay, the next step in extremizing this s is to integrate by parts to remove the dots from delta x and delta y. So the integration by parts brings in a minus sign. Notice the 1/2 cancels the factors of 2 here and here. So we have minus d by d lambda. That comes from the dot here that has been shifted over to the other side, acting on x dot divided by x dot squared plus y dot squared, square rooted. And that's times delta x. And from this term we have minus d by d lambda acting on y dot divided by the square root of x dot squared plus y dot squared delta y. And all of that is times d lambda. Okay, so now the argument is for delta s to be 0 with respect to arbitrary variations in x and y, then it must be the case that the coefficients of delta x and delta y must vanish. So this is equal to 0, and likewise d by d lambda acting on y dot divided by the square root of x dot squared plus y dot squared equals 0. Okay, so here are our two second-order differential equations for x of lambda and y of lambda. And in this case, it's not too hard to solve these equations. This equation tells us that x dot divided by the square root of x dot squared plus y dot squared is equal to some constant. And this equation tells us that y dot divided by square root of x dot squared plus y dot squared is equal to some constant. All right, if we take these two equations and divide them by one another, we find that y dot divided by x dot is equal to some constant. Okay, which in turn says dy dx is constant. So in other words, y and x are linearly related. Y is equal to some ax plus b. Okay, so what we find is that the geodesics, the curves that minimize or maximize the distance between points, those are the curves that make delta s equal to 0. Those curves are just straight lines in the Cartesian coordinates of this Euclidean geometry. Let's take a look at another example. What are the geodesics on the horse's saddle? Well, if I remember correctly, the line element for the horse's saddle looks something like 1 plus 4x squared dx squared plus 1 plus 4y squared dy squared minus 8xy dx dy. All right, so we would just consider some generic path or curve, x of lambda, y of lambda. Then dx can be written as x dot d lambda dy is written as y dot d lambda. And now we write down the distance between 2 points, lambda 1 and lambda 2. All right, this is the square root of ds squared, so that's 1 plus 4x squared x dot squared. The x dot squared coming from this dx squared, and I'll factor out the d lambda squared in the end, plus 1 plus 4y squared y dot squared minus 8xy x dot y dot. And then there's a common factor of d lambda squared in each of these terms, which factored out under the square root is just d lambda. All right, so to find the geodesics, we just need to extremize this expression, just like we extremize the action in classical mechanics. So we vary the action and write this as something times delta x plus something times delta y. Okay, we'll have to do an integration by parts on some of those terms to get rid of the dots from delta x and delta y. So these expressions in parentheses are what in classical mechanics would be Lagrange's equations when you set them equal to 0. And we set these equal to 0, and those are our equations of motion, our geodesic equations in this context. So these are the geodesic equations. As you can see, they will be second order differential equations, a system of second order differential equations. Now, they're going to be fairly complicated. It's probably not possible to solve them analytically, but you could solve them numerically. And in fact, you might be able to guess what some of the geodesics are by just remembering that this is a horse's saddle, and we have a fair amount of intuition for that shape as a surface embedded in flat Euclidean space. So I'll leave it to you to fill in the details of deriving the geodesic equations for the horse's saddle, and you can also try to guess some solutions and then just check to see if your guessed solutions satisfy the geodesic equations.